Video we are going to learn how to find this how to properly bias a BJT amplifier. Specifically, we are going to talk about the common emitter. So we wanted to make sure that we pick the values for RE, R1, RE2, R2, rather, sorry, and then RC. Okay, so given a load that we wanted to connect to the collector, so assuming that you wanted to design that IC VCC is less than equal to a value, for example, this is a power, right? Current times voltage is a power, so we want the power consumption, the power consumption less than equal to, for example, 2 milliwatt, right? So then given VCC, I know that IC must be less than equal to 200 divided by VCC. Assuming the voltage VCC in some volt. So let's say that you pick a value, right? So if I had VCC equal to maybe 16 volt, for example, then I have to pick IC to be 200, right? Less than equal to 200 divided by 16 milliamp. Okay, so once I have that value, and let's say that I'm able to measure the gain, the current gain of our amplifier, the BJT amplifier in the lab. You know that you can use a multimeter to do this, so you know better. So equal to, for example, 150. Okay, so once you have your VCC, you know better, and then you know IC, right? We also know IC. Let's say you pick your IC to be, for example, 1 milliamp. Okay, just an example. Okay, so then with these values, I can find the Thevenin equivalent connected to the base, right? So remember, the goal is to be able to find the DC operating point resistance values, right? So DC operating point resistant values. So if I find the terminal voltage seen at the base, right? So I call that VBB, and the terminal resistance seen at the base, I call that RBB. Then this will be connected to the base. Then I have RE here, and I have RC, this connected to ground. Okay, now, so this is the emitter, that is the collector, and this is the base. So my goal here is to be able to calculate the values of the resistances. So I will write KVL around the base loop. Okay, so I know the current here is IB, the current here will be IE, and the current here will be IC. So in a base emitter KVL loop, I have VBB equal to RBB IB plus VBE and plus RE IE. So, but we know that IE is IC plus IB, which is beta IB plus IB. So IE equal to beta plus 1 IB. Sorry. So when I substitute that in this equation, then I have VBB equal to IBB plus beta plus 1 RE. This is times IB plus VBE. And we know VBE equal to 0.7 volt. So assuming VBE equal to 0.7 volt, then we know we can calculate IB. So IB is equal to VBB minus VBE divided by RBB plus beta plus 1 RE. Okay, so having this, we know that IC equal to beta IB. So that gives me beta times VBB minus VBE divided by RBB plus beta plus 1 RE. So we see that this collector current, right? So ICQ, right, would depend on beta. So we wanted to design this ICQ, design the resistance values. Excuse me. So the goal is to design the resistance values for bias stability. Right, so we wanted to design ICQ, so ICQ does not really depend on beta. We want ICQ independent of the current gain beta. Okay, so we want ICQ to be equal to beta times, so we want, that's what we have currently, VBB minus VBE divided by, so RBB plus beta plus 1 RE. So we don't want beta in this equation. So what do? We are going to assume that if RBB is very small compared to beta plus 1 RE, then we can neglect excuse me, then we can neglect RBB in that equation. So that means we have beta. So if that's the case, if RBB plus beta plus 1 RBB is very small compared to this, then when I do RBB plus, when I add them up, beta plus 1 RE, right, that will be almost equal to beta plus 1 RE, right? Because RBB is very small even when you add it to beta plus 1 RB. Right, when if it's RBB is small compared to beta plus 1 times RE, so then when you add RBB to beta plus 1 times RE, that will be almost equal to beta plus 1 RE. So we have this VBB minus VBE divided by beta plus 1, so RE. And then we know that beta is large, right? It's large. So beta over beta plus 1 is almost equal to 1. So in this case, ICQ will be equal to VBB minus VBE divided by RE. Okay, so because beta over beta plus 1 is almost equal to 1, right? So if I had that beta over beta plus 1, and this is almost equal to 1. So the IC will be equal to VBB minus VBE divided by RE. So now, how do we pick the emitter resistance so that when we multiply that by beta plus 1 is large compared to RBB? So now we also know that when we have this configuration to find RBB, right, and as derived in the previous videos, RBB will be equal to the parallel R1 R2. So R1 parallel R2, so that is R1 times R2 divided by R1 plus R2. That was derived in one of the few of our previous videos. And the base voltage, we can do voltage division, which is R1 times VCC divided by R1 plus R2. Okay, so let's keep these two in mind, and then we are going to use them to compute the values of our resistances later on. Okay, so we have those values. So then when I go back to this equation, I know that RBB is small compared to beta plus 1 RE. So the rule of thumb will be to pick RB, right, 10 times RBB, right, will be equal to beta plus 1 RE, right? So you have to multiply RBB by 10, right, to be able to get the beta plus 1 RE. So it's small compared to it. So for example, if I take 1 plus 10, it's almost equal to, like, 1 plus 100. Let's do 1 plus 100. So 1 is 101. So the ratio is so now, so that means RBB is equal to beta plus 1 RE over 10. Okay, so that's how we are going to select the resistor value, the base. Okay, so let's say, and another rule of thumb, right? Well, this is a design question, right? It's a design choice, so you get you can make your own judgment, right? Engineering judgment about how you select this value. So I'm also gonna select my V E Q to be equal to 20% of VCC, right? So 20% VCC. So that means I'll have V EQ, which is 0.2 times VCC. So I also have this, right? I'm not saying this is a golden rule, but it works for me when I design this particular configuration, right, the command emitter. So given these values, right, so given that I know ICQ, right, which is 1 million, for example, 1 million, 1.5, as long as IC times VCC is less than the power consumption that you are given, then you get just find the resistance value that will meet the condition. So I have ICQ, which is 1 million. So then that means I know the VEQ, which is RE. Okay, IC, right? Because IC is almost equal to IE. So then I can find the collector the emitter resistance, which is 0.2 VCC that you're given, divided by IC, right, that you're designing around with. So I know RE. So that means I can find RBB. Okay, so now we can find RBB, right? So now we can find RBB. RBB. Right, so we know that RBB will be equal to beta plus 1 that I know from measurements in the lab, right? And then the RE that I just calculated divided by 10. Okay, so take this value, you plug that in there. Okay, so that's how I calculate my base resistance. Now that I know the base resistance, okay, I will calculate another base resistance, RBB, right? Is R1 parallel R2, which is R1 times R2 divided by R1 plus R2. So I'll use that because I know RBB, right? So then I can calculate R2. So how do we now? We're gonna calculate R2. So how do we calculate R2? We know that RBB equal to R1 times R2 divided by R1 plus R2, and the VBB is R1 times VCC divided by R1 plus R2. Okay, so we can use this equation there's two equations to find R2. So what do? I'll multiply this by R2 and this by R2. So then I have R2 VBB equal to VCC times RBB, right? Because this is equal to R1, R2, which is RBB. Okay, so R1 times R2 divided by R1 plus R2 times VCC, right? And I know that this, right, is equal to, and this is equal to RBB. Okay, so then what do? I'll just calculate R2 here, which is VCC over VBB that I calculated. Now, okay, so the question is, what is VBB? Okay, so let's calculate VBB. So RBB. Okay, so we know this is known and this is known. So we need to calculate VBB, right? So we need to now calculate VBB. So using that corrector, using the base emitter loop, we have VBB, right, which is RBB that I just calculated, okay, plus times IB plus VBE plus VEQ. Okay, so what is that equal to? I know RBB, just calculate RBB, right? We know VBE equal to 0.7 volt. We know RBB, which is given by beta plus 1 times RE over 10. Okay, and the only thing that I don't know here is VBB, right? I know also the IC, which is well, IB, which is IC over beta. So when we substitute all those values in this equation, then that's how we calculate VBB. Okay, so VBB is can be calculated by these three values, right? Plug them in, and then you know VBB. Now, so now that we know VBB, we can go back to our equation R2, which is VCC that we know, divided by VBB times RBB, right? So we know those values. So given that we know R2, now need to calculate, we can now calculate R2, R1, well, we know R2 already. Okay, so how do we calculate R1? We know that R1 times R2 over R1 plus R2 equal to RBB that was calculated above. So, okay, which is beta plus 1 times RE over 10 this we know. So need to calculate R1. So R1 R2 will be equal to RBB R1 plus RBB R2, right? Just multiply across. So then R1 times R2 minus RBB is equal to RBB R times R2. So then I can calculate R1, which is RBB times R2 divided by R2 minus RBB. So these are the values. So what we have left now is the collector resistance. So for the collector resistance, we can write the gain equation and use that to find that collector resistance. But I'm trying to not to record videos that are too long from now on. So this is going to be part 1. So in part 2 of this video, that's the next video, we are going to use the gain equation, for example, to find the appropriate value for RC, so that all this work together to meet the conditions. And then we are going to go back and check on the values, that we pick, right? So use those values. Maybe the 1 milliamp that we selected may not be the optimal value, so we could pick another value. But since we have these equations, we can put the equation on the spreadsheet. Then when we change, for example, IC is going to recalculate everything for us. Okay, so in the next video we are going to learn next video, right, we are going to learn how to, we're going to complete this because this video is like, I don't want to make it too long. So we're going to learn how to design the symmetrical gain, right, based off the voltage swing that you're given. So if you're given 10 volt peak to peak, then how do you design that swing? So we're going to use the low line and the key point to design the voltage swing, okay, and calculate the appropriate value for the collector resistance and a few other things to make sure that the design meet the requirement. So we're going to pull all these equations that we just derived with the remaining equation on the slide, on the spreadsheet, and then when we change one, we can also see what are the values for the resistance, so that will give us the design, right? So that will meet the requirements for the project. Okay, so please stay tuned for the next video, where we're gonna calculate the swing and a few other things.